Let us start with a brief recap of last class. Last class we looked at extrinsic semiconductors. Another name for these are doped semiconductors. Now the reason why we wanted to dope was because we found out that if you had an intrinsic or a pure semiconductor, the carrier concentration at room temperature was very small. Correspondingly, the conductivity was also small. For example, in the case of silicon, we found that the room temperature carrier concentration in an intrinsic semiconductor was only 10 to the 10 per centimeter cube, and the corresponding conductivity is very low, was around 3 times 10 to the minus 6 ohm inverse centimeters. So we wanted to increase the conductivity, so we selectively added impurities or dopants to the silicon in order to make it an extrinsic semiconductor. We also saw that in any semiconductor the law of mass action must always be satisfied, so that Np is equal to Ni square, which is a constant at a given temperature. This meant that we can either increase the concentration of electrons or increase the concentrations of holes. We cannot do both. So we also saw that there were two types of dopants. One was your N type, the other was the P type. We saw that an N type dopant was found in the caves of silicon by adding group 5 elements. The typical elements that we add are phosphorus, arsenic, antimony. All of these have one extra electron compared to the silicon atom, which means you have one extra electron in the conduction band. So these are N type. Similarly, we saw that we could form P type by doping with group 3, boron, aluminum, gallium and indium. These form energy states that are close to the conduction band in the case of N type, or close to the valence band in the case of P type, so that these are ionized at room temperature. So let us look some more today on the properties of extrinsic semiconductors. So far you only talked about silicon. So what about other semiconductor materials and doping in them? If you look at germanium, germanium lies in the same group as silicon. Which means all the elements that we used as dopants for silicon could also be used for germanium. So we can use your group 5 elements like phosphorus or arsenic as an N type dopant. Could also use your group 3 elements like boron as a P type dopant. Once again, in the case of germanium, we can calculate the ionization energies for these dopants. We could use the hydrogenic model. The only difference is the effective mass Me star for germanium will be different from that of silicon. And similarly, your relative permittivity for germanium, the value is around 16, while for silicon epsilon r is around 11.9. But we can use the same hydrogenic model in order to calculate the ionization's energies. So let us look at some actual values and just to compare silicon and germanium. Let us look at N type. Phosphorus, arsenic and antimony are your 3 dopants. Silicon and germanium. if we fill in the numbers, in the case of silicon we found out that the ionization energy in milli electron volts, so energy is in milli electron volts, was around 45, 54, 39. Similarly, in the case of germanium we will find that the ionization energies are very small, so this is around 12, 12.7, 9.6. If you remember, the band gap of germanium is also smaller, so at room temperature Eg for silicon is around 1.10 electron volts, Eg for germanium is around 0.67 electron volts. You can do the same thing with p type impurities or p type dopants. Boron, aluminum, gallium and indium. So, once again let me write silicon and germanium. 45, 57, 65, 157. Again we are writing Eg in milli, we are writing energy in milli electron volts. Germanium is around 10.4, 0.2, 10.8, 11.2. So, what this means is whether you have silicon or you have germanium, both lie in the same group. So, you can dope both of them in a similar fashion. If you want an n type dopant, you are going to add group 5 elements. If you want to add p type dopants, you are going to add group 3 elements. Usually the dopant concentration is very small. We saw earlier the case of silicon that your typical dopant concentration was around parts per million or parts per billion. So, parts per million is 10 to the minus 6, parts per billion was 10 to the minus 9, and even the small amount was enough to increase the conductivity by orders of magnitude. So, we saw for silicon, if I had an n type dopant with 10 to the 15 atoms per centimeter cube, which was approximately 20 parts per billion, your conductivity sigma went up to around 0.2 ohm inverse centimeter inverse. One thing we haven't looked much is how we actually do the doping. So, later when we look at the fabrication part, we will spend some more time on how we actually dope. But if you think of a parallel to metallurgy, one way we can think of is in the case of stainless steel or in the case of steel, we do something called carburizing, where we increase the carbon content. So, typically what we do is we have your sample at high temperature, you have a carbon source, so that the carbon then just diffuses into the surface and into the bulk of your steel. So, we can do something similar in the case of doping in semiconductors as well. So, if you want to dope n type, you have a source of your n type material. This could be in the gas phase, these could be ion implanted onto the surface. We will see what ion implantation is later, so that these can then diffuse into the surface and from the surface into the bulk. If you want to do compensation doping, we saw compensation doping last class, where you start with an n type semiconductor and then you make it p type by adding excess dopants of the other type. Similarly, in the case of compensation doping, you could take a small portion of your sample that is typically n type and add excess of p type. So, you could add excess of boron and then make it a p type semiconductor. These dopants are usually very stable at room temperature. Just to give you some numbers, let us take the case of silicon. I have two dopants, one is boron, one is phosphorus. Boron is a p type, phosphorus is n type. We can have, we will write down the values for the activation energy and the diffusion coefficients for these dopants. So, if I write D naught and EA is the activation energy for diffusion and D naught is a diffusion constant. So, in the case of boron, D naught has a value of around 0.76, activation energy is around 3.5 electron volts, phosphorus is 3.85, EA is around 3.6 electron volts. What this means is, in order to have boron or phosphorus diffusing into your material, you essentially need a high temperature process. The corollary of this is that at room temperature your doping concentrations are inherently very stable in the case of silicon. So far you have seen two semiconductors, silicon and germanium. You have looked at some examples of dopants, calculated the ionization energies. Since both silicon and germanium belong to the same group, we essentially use the same elements. Things become a little more complicated when we look at other semiconductors. So, let us look first at gallium arsenide. We saw earlier that gallium arsenide is an example of a 3-phi compound semiconductor. So, gallium is from group 3, arsenic is from group 5. The bonding in gallium arsenide is mainly covalent. But you also have some ionic character to the bond. Instead of gallium arsenide, if you have something like zinc oxide, which is a 2,6 semiconductor, there will be higher ionic character as compared to 3,5. So, it is also possible to dope gallium arsenide, but there are now more possibilities in this case. To understand this, let us go back to the periodic table, especially the portion around gallium arsenide. So, let me write the periodic table. We have done this earlier when we looked at elemental and compound semiconductors. So, group 2, 3, 4, 5 and 6, boron, carbon, nitrogen, oxygen, aluminum, silicon, phosphorus, sulfur, zinc, gallium, germanium, arsenic, selenium, you have cadmium, indium, tin, antimony, tellurium, mercury, thallium, lead, bismuth and polonium. So, this is just the portion of the periodic table around groups 3 and 5. So, the semiconductor we have is gallium arsenide, and we want to know what sort of elements could be added as dopants to gallium arsenide to make it p or n type. So, when we think of dopants, these are usually substitutional. Which means they are going to replace either the gallium or the arsenic atom. So, let us say I want to make an n type gallium arsenide. So, I would typically choose elements from group 6 because these elements have one more electron as compared to arsenic. So, if an element from group 6 replaces arsenic, we will have one extra electron, and if this extra electron is in a shallow state, if it is easily ionizable, it can get ionized to the conduction band and be available for conduction. So, to form n type, we are going to replace arsenic by group 6. We can use the same argument if you want to make a p type semiconductor. So, we replace gallium by any of the group 2s which has one less electron, or you have one hole. So, that will make it a p type. If you want to make something p type, you can replace gallium by group 2. Question is, what happens if you have a group 4 impurity? Let us say I have silicon. Now, silicon is an impurity in gallium arsenide. So, there are essentially two possibilities. The silicon can replace the gallium, the silicon can replace the arsenic, and depending on that you can either get an n type or a p type. So, if the silicon replaces the gallium, then silicon has one more electron because this is group 4, this is group 3. So, the extra electron is available for conduction, it will make it n type. On the other hand, if silicon replaces arsenic, it has one less electron and it will make it p type. So, silicon added to gallium arsenide can be either n or p type, and this type of doping is called amphoteric doping. This term ampho essentially means both, means you have the same element can act both as an n type or as an p type dopant. The only issue here, it is really hard to control the position of silicon. It is very hard to get silicon to selectively dope into gallium or to selectively dope into arsenic. So, if you have silicon as a dopant, it is very hard to control the type of dopant and the concentration of dopants. So, we saw that these are all the possible elements that can be used to dope gallium arsenide. The only other question is, where are the energy levels located? So, let me just do that by drawing the band gap of gallium arsenide. So, this is my conduction band, that is my valence band. The difference between the conduction band and the valence band is your band gap. In the case of gallium arsenide, the band gap is 1.42 electron volts. Also mark the center of the gap. So, if you look at the various elements, the group 2 and the group 6 elements, these will essentially form impurity states in the band gap of gallium arsenide, and depending upon whether they are n type or p type, they will be located either close to the conduction band edge or the valence band edge. So, if you look at the group 6 elements, these are n type. So, this one is sulfur, selenium is also very similar, tellurium is here. Again, all the dopant energies are in milli electron volts. Which means the diagram is not really to scale, but we will just show it semi qualitatively, so we have a rough idea. Silicon, we said silicon can go either to gallium or to arsenic. So, silicon as an n type is around 6 milli eV. Oxygen on the other hand is around 400. Similarly, we can look at the group 2 elements. So, we have beryllium, which is around 28, zinc is 31, cadmium is slightly higher, 35. We can also have silicon as a p type, that is around 35 again, carbon is around 26. So, if you have gallium arsenide, depending upon the type of impurity, we can either have both n type and p type. Similarly, for other 3,5 semiconductors, can once again have doping by choosing the appropriate group 2 or group 6 material. If you have a 2,6 semiconductor, something like zinc oxide or cadmium sulfide or cadmium selenide, similarly we can choose appropriate dopants to get both n type and p type. Most of what we have done here, so whether we are talking about silicon or germanium or gallium arsenide, we typically want single crystals of these materials. Whether we talk about an intrinsic semiconductor or whether we talk about an extrinsic semiconductor with dopants, we want an ideal single crystal with no defects. This is because whenever you have a polycrystalline material or if you have defects, so whenever you have polycrystals, you always have grain boundaries. Grain boundaries are a source of defects. You could also have impurities. You can have vacancies, dislocations, all of these are defects in your crystal, and whenever you have defects, you always have defect states. There are two types of defect states. One is shallow. Shallow states are those that are located either close to the conduction band or close to the valence band. So, they are close to the band edges. And because they are close to the band edges, they can easily get ionized at room temperature. So, shallow states mostly affect the conductivity, can either increase or decrease the conductivity. The other type of defect states opposed to shallow states are deep states. So, deep states are states that are located much closer to the middle of the band gap, or they are located far away from the valence band and the conduction band. So, in this particular case you have oxygen that is located approximately 400 milli electron volts or 0.4 electron volts below the conduction band. So, deep states are located close to the center of the band gap. Deep states can essentially act as traps for electron and hole. So, they could modify the conductivity, especially in the case of direct band gap semiconductors, where we are looking at optical properties. Deep states can also act as traps for these electrons and holes and then decrease the efficiency of any optical recombination. We will see defect states later when we also look at conductivity in an extrinsic semiconductor. The next thing we are going to do is look at how the Fermi level position changes in an extrinsic semiconductor. So, we want to find out the position of EF when you have dopants, whether you have p or n type dopant. In the case of an intrinsic semiconductor, we have electron and hole concentration to be nearly the same. So, we wrote an expression for the Fermi level position Eg over 2 kT So, this is for the case of an intrinsic semiconductor where N equal to P equal to Ni, and we found out that EFI is very close to the center of the gap. So, if NC and NV are exactly the same, is exactly EFI will be just Eg over 2, but if they are not the same, it will be slightly shifted from the center of the gap, but for most cases it is very close to the center. In the case of an extrinsic semiconductor, N is no longer equal to P. In fact, if we have an N-type semiconductor, we see that N is much larger than P. If you have a P-type semiconductor, P is much larger than N. So, in order to compensate for this difference in N and P, the Fermi level will also shift from the middle. One way to look at it or to calculate the shift is to use the equation for the electron concentration. So, let me start with an N-type semiconductor with Nd being the concentration of the donors. The donors are all completely ionized. So, the electron concentration same as the donor concentration. This we can write as Nc exponential minus Ec minus Efn over kT. So, Efn refers to the Fermi level position in the N-type semiconductor. So, we can take this expression and then rearrange the terms a bit, and what we will get is Efn minus Efi is nothing but kT ln of Nd over Ni. How we get this expression is that we start with this. We can write the same equation for intrinsic as Ni equal to Nc exponential minus Ec minus Efi over kT. So, we start with 1 and 2, and then we divide 1 and 2 and rearrange the terms to get the expression for the Fermi level position in an extrinsic N-type semiconductor with respect to the Fermi level position in an intrinsic semiconductor. You can write a similar equation for a P-type material as well. So, you have EFP minus EFI, which is minus kT ln of Na over Ni. So, the similar expression to this, except that in an N-type we have the concentration of the donors, in P-type you have a concentration of acceptors, and there is a negative sign here. So, let us do some numbers to get a sense of where the Fermi level is located. So, let us take N-type silicon with Nd is around 10 to the 15 per centimeter cube. We know the band gap of silicon Eg at room temperature is 1.10 electron volts. For simplicity, let us just say Nc is equal to Nv. So, the intrinsic position of the Fermi level EFI will be just Eg over 2. We know this to be 0.55 electron volts. Now, at room temperature you have all the donor atoms are ionized. So, N is equal to Nd equal to 10 to the 15 per centimeter cube. We will then use the formula that we just wrote down. So, that EFN minus EFI is kT ln of Nd over Ni. In the case of silicon, Ni is around 10 to the 10. So, substituting the numbers, this gives you a value of around 0.30 electron volts, or in other words EFN is EFI plus 0.30 electron volts, which is 0.55 plus 0.3 is 0.85. Adding an n-type impurity, so or adding a donor, shifts the Fermi level above the intrinsic level. If you want to show this in a band gap diagram, this is your valence band, this is the conduction band, this is the band gap. So, this is 1.10 electron volts. EFI is located at the middle. So, this is 0.55. So, you have added an n-type impurity. So, this creates your donor levels Ed. So, these donor levels are very close to your conduction band. At room temperature, all of the donors are ionized, and what we have is your Fermi level EFN located above the intrinsic level, but below your donor level. In the case of a p-type semiconductor, so let us do a situation where we have Na. So, it is a p-type, we just block it off with 10 to the 15. Instead of electrons you have holes. So, your hole concentration is 10 to the 15. Your equation becomes EFP minus EFI minus kT which is minus 0.30 electron volts, or EFP is 0.55 minus 0.3, 0.25 eV. So, in the case of a p-type semiconductor, you have the Fermi level located below the intrinsic level. So, depending upon the type of extrinsic semiconductor you have, you can either have the Fermi level shift up. If you have more electrons, it shifts up towards the conduction band. If you have more holes, it shifts below towards the valence band. So, all these calculations that you have done so far is for an extrinsic semiconductor at room temperature, where all the dopants are ionized, whether they be donors or acceptors. So, the next thing we are going to do is to look at how the dopant or how the carrier concentration changes with temperature. So, we want to look at the temperature dependence on the majority carrier concentration. So, it is a temperature dependence of N if it is an N type, or P if it is a P type. For simplicity, we are only going to look at the N type case, but whatever arguments we use for that, we can use the same for the P type semiconductor. How is this different if you have an intrinsic semiconductor? In an intrinsic semiconductor, we have essentially no dopants. So, the carrier concentration N equal to P equal to Ni for square root of Nc Nv exponential minus Eg over 2 kT. So, if you want to look at the temperature dependence of N, it is an exponential dependence on temperature. So, if you did a plot of the log of your carrier concentration over 1 over T, it is approximately a straight line as long as you assume that Nc and Nv are independent of temperature, straight line with slope Eg over 2k. This is as far as an intrinsic semiconductor goes. In the case of an extrinsic semiconductor, again that is an N type, you have essentially two sources for the electrons. You can get the electrons from the donor level Remember, the donor atoms each have one more electron than the silicon, that is why it is an N type. So, you can get the electrons from the donor level, and you can also get the electrons from the valence band. So, because you have these two sources, you have a different behavior for how the value of N changes with temperature. We are going to look at different regimes for that. So, the first case, let us look at a semiconductor at exactly 0 Kelvin. So, in this case you have an N type semiconductor at 0 Kelvin, there are no ionized carriers. You have a valence band that is full, and you have a conduction band that is empty, and you also have a donor level because it is N type, which is also full. So, this is my conduction band, this is my valence band, so that is full, that is empty, and these are my donor levels. The donor levels are located very close to the conduction band. I am just exaggerating the difference to show the fact that they are close to the conduction band. We can expand this portion of the diagram, so that now I will draw the conduction band, I will draw my donor level. At temperature equal to 0 Kelvin and at temperatures very close, you are going to have negligible number of electrons coming from the valence band. So, we can ignore the valence band totally and think of this as an intrinsic semiconductor. So, I will put intrinsic within brackets with the donor level acting as your valence band and the conduction band being the conduction band of silicon. So, all I have done is just expand this portion here and take it to be an intrinsic semiconductor with the donor level being the valence band and Cb being the conduction band of silicon. At 0 Kelvin you have a donor level that is completely full, you have a conduction band that is empty, and then you will have your Fermi level in between the conduction band and the donor level. Now, if you start to increase your temperature from 0 Kelvin, electrons are going to get excited from the donor level to the conduction band. Once again, your temperature is low enough that you can ignore any contribution from the valence band of silicon. So, we do this till some temperature which we are going to call Ts, or a saturation temperature. So, a temperature is above 0 Kelvin, but it is below a certain temperature called Ts. We are going to define Ts as saturation temperature. In this particular regime, you are going to have electrons from the donor level getting ionized into the conduction band, and this process is going to happen till all the donor atoms are ionized. So, the saturation temperature is defined as the temperature in which the donors are 90% ionized. Some books will give you a definition of 99% ionized, but we will just use 90% here, at which donors are in order to calculate the value of Ts, we look at the expression for the electron concentration. We will treat this material as an intrinsic material with the donor level being your valence band. In this case, N is 1/2 Nc. Instead of Nv, you will have Nd, which is your donor concentration, exponential minus Ed over 2 kT. The 1/2 term is here because your donor levels are localized levels. Your donors are localized levels, so they can only take one electron of a normal band can have 2 electrons of opposite spin. Because your donors are localized levels, they can take only 1 electron, which is why we have the term 1/2. So, we are treating this as an intrinsic, with Ec being your conduction band and the donor being the valence band, and at the saturation temperature N is 90% of Nd. We can put this value here and try and solve this expression for Ts, and if we do this, we get a value of Ts to be approximately 32 Kelvin. So, in this assumption we take Nc to be independent of temperature. If you take in the temperature dependence of Nc, you will get a Ts of around 60 Kelvin, but either way the number is much below room temperature, which is around 300 Kelvin. What this means is, at a relatively low temperature, in the case of silicon, you have a situation where the donors are completely ionized. So, we started at low temperature, where we said that we will ignore all the electrons coming from the valence band. We found out that as we started going above 0 Kelvin, electrons are going to get ionized from the donor levels till we reach a saturation temperature when almost all the donors are ionized. So, above the saturation temperature, all the donor atoms are ionized, so that N is nothing but Nd, and P would be Ni square over Nd. Ni square over N, which is nothing but Ni square over Nd. Now, if we keep increasing temperature further, there is going to come a point when electrons are starting to get ionized from the valence band. In this particular case, the semiconductor now behaves as an intrinsic semiconductor, and we define this temperature as Ti. So, we define Ti as the temperature when N is equal to 1.1 Nd. So, you have extra carriers that are now coming from the valence band of the silicon, and this makes it an intrinsic semiconductor. So, we had two temperatures, Ts and Ti. So, Ts was 0.9 Nd, Ti is 1.1 Nd. So, we have a regime where the carrier concentration varies within 10%. If we want to calculate the value of Ti, the intrinsic temperature, we can look at the numbers. So, N is 1.1 Nd, and we are going to treat this as intrinsic. In any semiconductor, the total charge should be balanced. So, N is equal to P plus Nd, so that P is 0.1. We also know that Np is Ni square, and then doing the math we get Ni to be 0.33 Nd. So, N is 10% more than your donor concentration, and at that temperature Ni is approximately 0.33 Nd. We can use this expression Ni equal to square root of Nc Nv exponential minus Eg over 2 kT, but now the temperature will be Ti, which is your intrinsic temperature. Can substitute in the values. Once again we will assume that Nc and Nv are independent of temperature. That gives you a Ti of approximately 584 Kelvin. If you try to convert that into degrees, this is approximately 310 degrees. Above this temperature, the semiconductor essentially behaves as an intrinsic temperature. So, in the case of silicon, we have a regime starting from the saturation temperature, which is around 50 Kelvin or 60 Kelvin, to an intrinsic temperature that is around 584 Kelvin, where the carrier concentration is essentially a constant and it is equal to the donor concentration. The difference is only within 10%. This means the conductivity will also be very stable, because the conductivity depends upon the carrier concentration. If we put these numbers together and did a plot of the log of the carrier concentration versus 1 over T, we can compare that to your intrinsic semiconductor. In the case of an intrinsic, we have already done this before. Log of n versus 1 over T is just a straight line with one slope. So, this is intrinsic. You can do the same for extrinsic. So, now instead of one slope we will have two slopes and we have three regimes. In this particular case, since this is 1 over T, this is low temperature, this is high temperature. So, at low temperature you have electrons coming from your donor level. So, you have a straight line with a slope that is given by your donor ionization. Then we have a situation where the donors are all ionized and your carrier concentration is almost a constant. At some high temperature we are going to get new carriers from the valence band. The material behaves like intrinsic. So, this is minus Eg over 2k. So, we have three regimes: an ionization regime, a saturation regime where the carrier concentration is almost a constant, and then finally an intrinsic regime where the material starts to behave like an intrinsic semiconductor. So, we will stop here for today. In the next class we will look at how the conductivity changes as a function of temperature, and we will also look at the effect of doping on the mobilities of electrons and holes.